And oh, one other point, which is not really related to this class, but I don't know if any of you noticed, but this morning I skipped an example problem because I was thinking, oh, I'm done with chapter 12 in dynamics, and I started to collect up the problems, the solutions, to scan them, and realized, oh, I forgot to do one of the sample problems. So we'll cover that on Wednesday in dynamics. But I don't know if any of you noticed, but I didn't actually notice till after the class was over and I went to collect the problems. All right. So we had just discussed, oops, wrong button. We just discussed figuring out and using torque and to determine internal stresses. What we're going to look at here now is we have a steel shaft, right, and an aluminum tube. So notice how this is what it looks like from a cross section, and this is what it looks like. We've got the steel shaft in the middle. We've got an aluminum tube on the outside, right, that is around the shaft, and they're both the same length, and they're both on a fixed support, and they're both attached to this rigid disc, right? And it says, knowing the initial stresses are 0, determine the maximum torque T naught that can be applied to the disc if the allowable stresses are 120 megapascals in the steel shaft, right, and 70 megapascals in the aluminum tube. And they give us the stiffnesses, use G is 77 gigapascals for steel, and G is 27 gigapascals for aluminum. We're also given dimensions here, right? The steel rod is solid, it's 50 millimeter diameter, OD. And then the the aluminum shaft is a 70, oh, that's an odd. It's 76 millimeter OD with an 8 millimeter wall thickness. This is common for tubes. A lot of times you'll get this type of information. You'll get an OD and a wall thickness. That's typically what they control in extrusion dies when they make tubing and stuff, is they'll control OD and wall thickness, based on the die. All right, so let's work on this problem here. Now you can kind of see from these images, I took these right out of the book, but you can kind of see we're going to look at the torques, torque 1 and torque 2 on each of these. So let's see how that's going to look on a piece of paper here. So the first thing I'm going to do is I'm going to draw a free body diagram of this disc on the end. And I'm going to draw it like this. So let's just say FBD for disc. All right, that's the disc here. Let me just label this disc. And it's going to look like this. It's going to be a circle. And we're going to have, we're going to apply a torque. Let's see, determine the maximum torque T naught that can be applied. And it doesn't tell you clockwise or counterclockwise. So whatever you, whichever direction you feel like it, you can draw it out. Just watch your signs and directions, right? So this applied torque, let's see, applied torque T naught, put that in parentheses, is resisted by both the shaft and tube, right? So let me I'm going to draw those out as the opposing torques, right? We've got, I'll number from the left to right, T1 and T2. These opposing torques are a result of, the stiffnesses of these, the rod and the tube. But we don't know the portion of torque carried by each. Oops, there should be two R's. Carried by each. Right, we don't know yet. Well, we'll figure out how to find out. We don't know what the T1 and T2 are, right? We don't know if T1 is half that of T2 or if, whatever. However, the angle of twist is the same for both tube and shaft, right? Because they're welded to the plate, we know that the angle of twist is the same for both of those. The assumption here is obviously that the weld is not going to crack, right? That they're both seeing the torque T naught, and they're both being twisted. And let's write that out. So phi1 equals phi2. Phi is the angle of twist. And based on the equations for the angle of twist, we know the angle of twist is the torque times the length divided by the polar modulus here. Let's see, J1 and the stiffness G1 equals, right, so they're going to be equal to each other. All these things are different except for length, right? L1 equals L2. So we can cancel that out, right? Because they're both the same length from the rigid surface to the disc. The torques we don't know. The stiffnesses we were given. The polar moments of inertia we can calculate. J1 is just let's use let's number these in here. 1 and 2. So I'm going to go with 1 is the solid shaft and 2 is the hollow tube. So J1 is going to be pi over 2 times the radius, 0.025 meters to the fourth. I'm going to put everything in terms of, let's see, meters. I could have used millimeters. We got gigapascals. Now let's stick with meters because that's how I have it in my notes. You're either stuck with working the numbers that are too big or too small. So this is going to be 6.136 times 10 to the minus 7th meters to the fourth. And what is J2? J2 is pi over 2. We've got 0.038 to the fourth minus 0.030 to the fourth. And this gives us 2.003 times 10 to the minus 6 meters to the fourth. So again, I just converted everything to meters for the sake of this this problem. A little line here. I'm trying to fit this all on one page. So all I'm doing here is using these to set the equations equal to each other. Now I can come up with a relationship between the two torques. by writing this out. So I'm going to write the T1 over, let's see, J1, I've got 6.136 times 10 to the minus 7th meters to the 4th. Here I've got 77 gigapascals. And this is equal to T2 over J2 G2, so that's 2.003 times 10 to the minus 6th. And G is what? G is 27 gigapascals. Oh. For this, I mean, basically all the units cancel out. So I wasn't really, really too concerned at this point. T1 is going to be equal to 0.874 T2, right? So T1 and T2 are related this way through the angle of twist. So now the question is, which part reaches critical stress first? And we have two different critical stresses. Did I do the steel? Let's see, shear stress in the steel. Let's see, one critical stress is, allowable stress is 120 in the steel and 70 megapascals in the aluminum tube. Let's work with the aluminum first. So the shear stress in the aluminum needs to be less than or equal to 70 megapascals, right? So that's T2 is equal to, so now this is taking and just basically reversing the equation for shear stress and torque. Let me see, it's probably in the, yeah, this equation right here, right? So I'm just taking the torque, I'm solving for what is the torque if I know the limiting shear stress. So I'm just going to rearrange that. And I'm going to know the radius, and I'm going to know the polar moment of inertia. So the torque that the aluminum tube can take is equal to the allowable shear stress. We've got J2, which is the polar moment of inertia for that one, and C2. So that is 70 times 10 to the 6th newtons per meter squared. Remember, I had the polar moments of inertia in meters, so I'm going to just work in meters here. I've got 2.003 times 10 to the minus 6th meters to the 4th. I've got a radius of 0.038 meters. Well, sometimes you got to choose your battles with the units. Let's see, so 70, for some reason I didn't calculate this out. E to the 6th times, so we got 2.003 e to the minus 6 divided by 0.038. Yeah, 3689. This turns out to be 3689.7. What are the units on this? We've got newtons stays, right? Oh, we got newtons. Okay, yeah, we're going to cancel out 3 newtons here. These, and we're left with that one. right? So Newton meters, which is what a torque should be, right? This is why doing your units is a good way to check all your, check you got things going in the right way, you know, did you rearrange the equation correctly, right? Torque is a force times a distance. All right, so this is torque 2. So I'm gonna round this. Torque 2 is equal to 3690. From the relationship, right, from the angle of twist relationship, T1 is equal to, so I'm going to take that times 0.874. So it's like 32. I'm going to round up again to 32.25 Newton meters. Right. This is just, I've calculated T2. I know that T1 is always 0.874 of T2, so I can get a torque for that. This is a torque that gives me the maximum shear stress in the aluminum. This is for tau max in the aluminum. What is the shear stress in the steel? Right, so we're just starting from one point. You could have chosen your steel up here and worked the other way. The point is that we know for the aluminum that the maximum allowable shear stress is 70 megapascals. So we figured out what the max torque is. This is okay for the aluminum. Now we got to figure out, okay, what's okay for the steel is, and we know the relationship from angle of twist. Due to the stiffnesses of these things, the torque is going to be split up such that T2 is 3690 and T1 is 3225. So this is the torque in the steel. So for the steel, the stress in the steel is just going to be the torque times the radius divided by the polar moment of inertia. And for this, we wind up with 3225 Newton meters. Our diameter of the steel tube is 50 millimeters, so that gives us a radius of 0.025 meters, divided by our polar moment of inertia, which we calculated as 6.136 times 10 to the minus 7th meters to the 4th. All right, I better check these numbers because I have some crossouts here. 320, 3225 times 0.025 divided by 6.136 minus 7. Oh, yeah, that's a big number. I can see why I had the crossouts. 1, 2, 3, 4, 5, 6, 7, 8. Yes, it is 8. All right. So I'm going to call this 1.31. I'll round it here, 1.314. That looks like a good place to round. Times 10 to the 8th. And our units on this are newtons per meter squared, which is equal to, this is equal to a Pascal. This is obviously more than enough to get to a megapascal, right? A megapascal is times 10 to the 6th. So here we've got 131.4 megapascals, right? So, oh, what's going on here? what is the allowable stress in the steel? The allowable stress in the steel was 120 megapascals. Oh, so we've exceeded the allowable stress in the steel. So let's write this out here. The stress in the steel is equal to 131.4 megapascals, which is greater than 120 megapascals, right, which is the limit. So the steel is the limiting component. So now what we're going to do is we're going to go back and do the same thing we just did for the aluminum, right? We're going to calculate, except we're going to calculate torque 1 now. So torque 1 for the steel is equal to the allowable shear stress for the steel times the polar moment of inertia over the radius, right? And that allowable was 120 megapascals. So I'm going to put that up here in units of Newton per meter squared. Polar moment of inertia, we calculated up there. Oh, we used it up here too. 6.136 times 10 to the minus 7th meters to the 4th. And the radius is 0.025 meters. Right, basically just this equation rearranged again. And from this, we wind up with, it looks like I got 2945 Newton meters. And this is for T1. So T2, right, T2 is just T1 divided by 0.874. So for T2, we're going to wind up with 3370 Newton meters. And I'm guessing I just rounded off to the nearest Newton meter in all these. So the max torque ooh, I forgot to write the equation up here. Go back up here. T naught is equal to T1 plus T2, right, in terms of magnitude. They're equal opposite directions. So the max torque is going to be T1 plus T2. So T naught is equal to 6315 Newton meters. So again, this is sort of working off of the additive effect of torque. This is where the course is so much different than statics. Is you have to actually sit back and think about limits, right? Is this steel shaft going to, is this allowable stress okay, right? You can solve the problem either way. It's just in one case, the torque is too high, right? If we had used, well, we can see. We started off with aluminum. We found out what the torque was to generate the maximum shear stress in the aluminum. This is the maximum allowable shear stress in the aluminum, 70. So we use that as a limit. We said we want to stay below that value. Maybe our initial assumption was based on, oh, you know, aluminum tends to be weaker than steel, you know, whatever. Who knows where that assumption came from, right? But you have to assume something. You have to start with one of the components. And if you had started with steel, you would have started off with 120, right? And then you would have checked it. And you would have seen that the shear stress for aluminum was less than the maximum for the aluminum, and then you would have been fine. But in this case, we found the torque in the aluminum as a function of the aluminum bar's polar modulus and radius. And remember, the polar modulus, well, let's see. We don't actually need the stiffness down here. The stiffness is only telling us the relative proportion that each of those components is taking up of the torque, right? And then down here is where we find out what's the actual stress in those components and how do we back out the max torque based on those allowable stresses. So yeah, any questions about this problem here? I'm going to put this one away. Flip back to the PowerPoint for a minute. All right. So that was this problem. I'm going to leave this up while I put this away, and then we'll talk about designing shafts. Let's see. So the example for this is labeled some weird number. Well, let's go through the slides first. So now we have enough information, well, at least stress-wise. Let's look at how we would design transmission shafts. So, I mean, this is going to be common, or this is common in industry, right? You've got shafts that transmit power for, from motors to some process, from generators to something else. Or not from a generator. Generator typically generates electricity from a turbine to a generator, right? You need some kind of shaft that goes, connects whatever component you're using, whatever pump component you're using in the working fluid, that needs to connect back over to the generator and spin the generator. And typically, you're going to be looking for things like power and speed of rotation. So you may have to meet certain power requirements, right? And that generator's gonna have to turn a certain speed. So you're gonna have to select your shaft material and design cross sections so that you don't exceed certain shear stresses, right, in that material. Let's see. This is the equation for torque. Torque applied to a shaft. So yeah, so let's look at this. This is power is torque times your angular velocity. And this is radians per second. You're going to see, I wrote this all out because you're going to see this come up a bunch of different ways. A radian per second can be converted into a frequency, hertz, by multiplying by 2 pi. Right? Because what is this saying? This is saying that you're going radian per second, you're converting it basically to revolutions per second, right? And a revolution per second is basically, you'll hear it often referred to as hertz, right? Oh, it's 60 hertz, 70 hertz, whatever, 120 hertz. And then the torque is just the power, just rearranging this, power over the angular velocity. So power over the 2 pi f, where the f is the frequency. Yeah, so the 2 pi just converts from revolutions to or per second to radians per second. Let's see, shaft cross section. Shaft cross section, you're going to be asked many times. Well, this will be something that comes up, right? What's the shaft cross section that will not exceed the maximum allowable shearing stress? So remember, we learned that the max shear stress occurs at the max diameter. So that's going to have and whether or not you use a solid shaft or a hollow shaft is going to affect that, right? So we start off with our equation that we have. Our max shear stress is equal to torque times radius over polar moment of inertia. And we can rearrange these to find, well, let's see, in this case, we're rearranging it to find C, well, sort of. J over C equals pi over 2 C to the cube, right? So this is for solid shafts. All they're doing here is they're taking the J. Remember, J is pi over 2 times the radius to the 4th. Well, we know that the maximum allowable shearing stress occurs at the point where the radius is maximum, right? So where R equals C. So here they just substituted in J is pi over 2 C to the 4th, and that divided by C reduces to this. And so you can set this equal to the torque divided by the max shear, and you can solve for your radius. However, for hollow shafts, if you do that, right, you get pi over 2, and you wind up with this equation, right? C2 minus C1. The maximum shear stress is going to occur at the maximum diameter, right? The maximum radius, C2. But C2 minus C1, right? There's an inner radius on all these hollow tubes. So you need to keep that in the equation. Now, you may be given some relationship between these radii, right? Like if you know the wall thickness, you can say, okay, C1 is just C2 minus whatever. You may know the ratio, right? If someone tells you the ratio, C2 is 1.1 times C1, or C1 is 0.8 times C2, right? So you can plug those numbers in, and that's for hollow shafts. All right, so let's do this concept application. I mean, that's really all you need to know on top of all this stuff is the whole power equation. Right? This is just a rearrangement of, right, polar moment of inertia. So you just don't know what that is because you're solving for C. Should I go through and derive that again? Yeah, let's just do this problem. What size shaft should be used for the rotor of a 5 horsepower motor operating at 3,600 RPM if the shearing stress is not to exceed 8,500 PSI in the shaft? All right, so I put this in on paper. I'm going to sketch this out so we have something to look at here. Rotor of a 5 horsepower motor. And so this is oh, it was going better than I expected, didn't I? Messed it up. So this is your 5 horsepower motor. And this is your shaft here, right? And let's just make a red line. And then this is going to be rotating at 3,600 RPM. And tau max needs to be less than or equal to 8,500 PSI. All right, so what is this? Let's rewrite this in terms of the torque. So tau max is equal to torque times C times J. So what are these things? This is unknown, right? This is the radius. Unknown radius. This is the polar moment of inertia for a solid shaft. Maybe I should put a 4 solid shaft. It's going to equal, right, pi over 2 C to the 4th. So we need T. We're looking for this. We can calculate this. Well, This is going to be part of C. We need to find torque, plug this in there. So then we can find the max, or we can find what C is from this. Let me just rearrange this first. So I'm going to write this out. Tau max equals, we've got TC over pi over 2 C to the 4th, right? And you can see here the C is going to cancel. We're going to have a 3. We want to find C. So C is just going to be equal to the cube root of, what are we going to have? We're going to have 2 over pi times the, oops. Oh yeah, that's right over here. This goes over there, this goes over here. We have torque on top, and then we'll have shear stress on the bottom. Right, so we need to find, we know what tau max is already, 8,500 PSI. We need to find T. Oh, this should be a cube root as well. All right, so first of all, I didn't write the equation for it. Let me go back to the slide. I don't like the way I did this. Let me write this down. T is power over angular. Oh, I did write that down. All right, I have that. So tau is going to be, or sorry, torque is going to be power over the angular velocity. And this is also equal to power over 2 pi f. Right. Now we got to do some conversions here. We were given this has to transmit 5 horsepower. A lot of the information we have is we're going to be working backwards. We want to get some dimension of this. And we need to know some kind of power in terms of length units, right? So I'm going to introduce you to a conversion factor. 6,600 inch-pound seconds. So inch-pounds per second is in 1 horsepower. That's 1 horsepower. So the power that we're transmitting is 33,000 inch-pound per second. This is a conversion factor right out of your textbook, 6,600 inch-pound second, and I got to remember to give this to you if I ever give you a problem like this, because I really don't want you spending time looking for a conversion factor. Omega is 2 pi radians per 1 revolution times 3,600 revolutions per minute. Right, that's what we were given, 3,600 RPM. We got to convert this over to omega. So I should have written them backwards. 3,600 revolutions per minute. 2 pi radians is 1 revolution, and then we're going to convert that from minutes to second. 1 minute is 60 seconds. Right, so from here we've got 377 radians per second. Right, this is the speed, the angular velocity, basically. This is the power we're transmitting in some units that we can actually get a length out of. Now, if we didn't do this up here, we'd have to do it later anyway, once we had horsepower in the equation. We'd be like, oh, how many inches is that? How many feet is that? I have no idea. You might see a conversion factor for foot-pound seconds as well. All right, so now I'm going to figure out the torque. The torque is the power, 33,000 inch-pound per second, divided by 377 radians per second. And the radians per second goes away. We're left with 87.53 pound inch. That's our torque. Ooh, we're almost done. So now we're going to figure out the radius from up here. I've got the cube root of 2. I'm just going to leave the split up the equation. I've got the torque on top, 87.53 pound inch, divided by pi times 8,500. In this case, it's PSI, pounds per inch squared. All right, that's our, this is the information you're given, was what sort of defines what units you want to work in, right? I mean, I could have used foot-pound seconds, but that's not gonna, I still need inches in the end. Or I need to convert RPM to, or sorry, pound per square inch to pounds per foot square. So here I get 0.187 inches. Now, the shaft diameter equals, so this is, remember, this is a radius. Radius, don't forget that. If I multiply this by 2, I get 0.374 inches. So a shaft of 3/8 inch should be used. Notice 3/8 inches, 0.375 inches. I went up to the nearest round shaft diameter, right? What's the nearest shaft diameter? So if I tell you round up to the nearest 1/8 inch or millimeter or whatever, round your value up, okay? 374 inch. All right, so that's basically shaft design. Now, again, the one thing I do want to point out here is if I were to give you a hollow shaft design, right, you would have J here would have both the outer radius and the inner radius. So C1 and C2. I would have to give you some other piece of information to relate the two radii, right? Like I'd have to give you the ratio, or like C1, or the inner radius is 8/10 of the outer radius, or you know, the wall thickness. So I need to give you some extra piece of information. But you could design a hollow shaft the same way. Is this process, just knowing that information. All right, so we'll end here for today, and I'll see some of you in circuits, and I'll see the rest of you in dynamics on Wednesday.